What specific problem does the absolute zero paradigm aim to address in the context of scalability and reasoning model training?
The absolute zero paradigm aims to address the scalability issues inherent in existing reasoning model training methods, particularly those that rely on human-curated datasets. Traditional approaches, such as supervised fine-tuning, SFT, and reinforcement learning with verifiable rewards, RLVR, depend heavily on expertly curated distributions of reasoning question-answer pairs, which raises concerns about sustainability as the demand for large-scale, high-quality datasets grows. The absolute zero paradigm eliminates this dependency by enabling models to autonomously propose and solve tasks through self-play, thereby allowing for continuous self-improvement without external data. This approach not only mitigates the bottleneck of data curation, but also prepares AI systems for a future where they may exceed human intelligence, fostering their capacity for autonomous learning and growth. Ultimately, Absolute Zero represents a shift towards a more scalable and self-sufficient training framework for reasoning models.
How does the proposed Absolute Zero Reasoner, AZR, work? Illustrate the process step by step, detailing the roles of proposer and solver within the training framework.
The Absolute Zero Reasoner, AZR, operates within a self-play training framework where a single model assumes two roles, proposer and solver. First, the proposer generates a task conditioned on a variable that reflects past task examples, aiming to create a valid reasoning task that can be verified by the environment. This task consists of a triplet, program, input, output, and is validated through execution to ensure correctness. Once a valid task is established, the solver receives the task and attempts to produce the correct output, receiving feedback based on the accuracy of its response. The model is trained using reinforcement learning, where the proposer is rewarded for generating learnable tasks, and the solver is rewarded for producing correct answers, facilitating continuous improvement through self-generated tasks and interactions with the environment.
Can you provide a simple example that illustrates how AZR generates a coding task and solves it, highlighting the reasoning modes involved?
The Absolute Zero Reasoner, AZR, generates a coding task by first proposing a program and an input, which are then validated to form a complete triplet, program, input, output. For instance, in a deduction task, AZR might propose a program, P, that calculates the area of a triangle given its base and height, along with an input, I, representing specific values for these parameters. The environment executes the program with the input to produce the output, O, completing the triplet, PI-O. In solving this task, AZR predicts the output, O_pi, based on the proposed program and input, verifying its correctness through type-aware value equality in Python. This process exemplifies the deduction reasoning mode, where AZR engages in step-by-step logical reasoning to derive the output from the given program and input.
What are the theoretical or practical benefits of using AZR over traditional reinforcement learning methods with expert curated datasets?
The Absolute Zero Reasoner, AZR, offers significant theoretical and practical advantages over traditional reinforcement learning methods that rely on expert curated datasets. Firstly, AZR eliminates the dependency on human-generated data by allowing the model to autonomously propose and solve tasks through self-play, which enhances scalability and reduces the effort required to construct large-scale datasets. This self-sufficient learning mechanism enables AZR to adapt and evolve in open-ended environments, unlike traditional methods that are constrained by fixed human-designed tasks. Practically, AZR has demonstrated superior performance, achieving state-of-the-art results in coding tasks and competitive performance in mathematics without any in-distribution data, highlighting its ability to generalize reasoning skills effectively. Additionally, AZR's design mitigates issues such as hacking with neural reward models by relying on verifiable feedback from the environment, ensuring more stable and reliable training outcomes. Overall, AZR represents a promising shift towards more autonomous and scalable AI systems capable of achieving superhuman reasoning capabilities.
What metrics or benchmarks were used to validate the performance of AZR, and what were the key results that demonstrated its effectiveness?
The performance of the Absolute Zero Reasoner, AZR, was validated using various benchmarks categorized into in-distribution, ID, and out-of-distribution, OU datasets. For coding tasks, AZR was evaluated on the HumanEval Plus and MBPP Plus benchmarks, while for mathematical reasoning it utilized standard benchmarks such as AMY24, AMY25, and OlympiadBench. Key results demonstrated AZR's effectiveness by achieving state-of-the-art performance in both the 7B overall average and coding average categories, surpassing previous models by 1.8 absolute percentage points, and outperforming models trained with expert-curated human data in coding tasks by 0.3 absolute percentage points. Additionally, AZR models exhibited strong cross-domain generalization, with significant performance gains of 10, 9 and 15, 2 percentage points in math after training, compared to minimal improvements from expert code models. These results highlight AZR's capability to excel in reasoning tasks without reliance on human-generated data.
What limitations did the authors acknowledge regarding the absolute zero paradigm, and how does this impact its applicability in real-world scenarios?
The authors acknowledged several limitations regarding the absolute zero paradigm, particularly concerning its reliance on the environment for feedback, which may not always provide sufficient or accurate rewards for complex tasks. They noted that while the model learns through self-play, the absence of human-curated data could lead to challenges in task validation and the generation of meaningful tasks, potentially limiting the model's effectiveness in real-world applications. Additionally, they highlighted the risk of the model producing concerning chains of thought, termed OO moments, which raises safety and ethical concerns about deploying such systems autonomously. These limitations suggest that while the absolute zero paradigm shows promise for autonomous learning, its practical implementation may require further refinement to ensure reliability and safety in diverse real-world contexts.